Unlike previous chapters, in which we jumped right into section 15.1, for this chapter we're going to begin with an introduction to analytic geometry. I think that if we go through the concepts of our chapter conceptually before we start applying algebra to them, and this new notation we're going to wind up using, we'll have a much easier time solving our problems because it'll make more sense to us what they mean. So first, what is analytic geometry? Analytic geometry is a form of math which takes geometry, which is the dominant form of mathematics for 2,000 years, and allows us to use algebra to solve geometric problems. So, a big advance in analytic geometry was initiated by the French philosopher and mathematician René Descartes. He is the one who invented what we call the Cartesian, after him, the Cartesian coordinate plane, which we think of as just the xy axis. And now, of course, these are totally ubiquitous in our society. We see graphs everywhere, and the use of an xy axis to represent things. But when Descartes started using them, this was brand new, and the legend is that he came up with this essentially on his own, that he had this insight, that we can represent geometry problems on a plane like this. And we can also represent algebra problems geometrically on a plane like this. So those are the two things that analytic geometry allows us to do. It allows us to represent geometry problems with algebra, which is really helpful because frequently numbers are easier to work with than shapes. And as we've seen this whole year, we've used a lot of algebra when solving geometry problems, and it's made solving geometry problems significantly quicker and easier than it would be writing out complete English sentences in ordinary language to figure out the solution to a geometry problem. Similarly, analytic geometry allows us to represent algebra graphically. It allows us to represent an algebra problem in a geometrical figure. And that's really useful because it gives us a visual representation of algebra. In this chapter, we're going to learn how to do such things as find the length of a line segment on a coordinate plane by turning it into a right triangle. We'll learn how to find the slope of a line on a coordinate plane. We'll learn how to find the distance between a point and a line. And we'll also learn how to recognize an algebra problem which describes a circle on a coordinate plane. And that's really helpful. So that in the future, when we see algebra problems, we know what they would look like if we were to graph them. So let's take an easy algebra problem and represent it graphically. Let's say y equals x. So that means if y equals 1, what does x equal? X also equals 1. If y equals 4, what does x equal? That equals 4. And if y equals negative 2, what does x equal? They're both negative 2. And there we go. We can connect these, and then we can connect these points. A visual representation of the equation y equals x. Let's try a slightly harder algebra problem and visually represent it. If y equals x plus 2, when y equals 0, x equals negative 2. When y equals 4, x equals 2. When y equals negative 4, x equals negative 6. And we can connect these lines, and there you have our graph. You'll notice something interesting, that it looks like our magenta line and our orange line are parallel. We'll also be investigating parallel lines in this chapter. Let's do one more. Let's say 5y equals negative x. So let's just plug in numbers for y like we've been doing. Let's say y equals 0. Then x equals negative 0, also known as 0. How about when y equals 1? When y equals 1, x is negative 5. How about when y equals negative 2? When y equals negative 2, x equals 10, something way out here. And so there's the slope of that line. So you can start to get a sense of how this works by making up your own equations and drawing the line that represents them. Alright, let's look at some other examples and reason through them. Let's look at this light blue line, which you see, and it goes from 0, 0 to 1, 1. What's its length? Well, notice that it's in a box. It's in a square that's 1 by 1, and it's the diagonal of its square. It's root 2. Let's look at the red line. What's the length of this red line? Similarly, we're in a box that's 2 units by 2 units. And so, looking at our rule for 45, 45, 90 triangles, we know that this is 2 root 2. But now let's make things a little bit harder. Consider the lime green line. How can we find its length? So we have our start point at 0, 0, and an end point at 2, negative 4. If we can form a right triangle using this line, then we'll easily be able to find its length. So we'll make a right triangle here, and then we'll be able to find the length of this hypotenuse line. So the leg on the left that goes vertically, what's its length? Its length is 4. And what's the length of this horizontal line on its other leg? That is 2. And then we can use the Pythagorean theorem to find that line. And the key trick here was to make whatever line we wanted to find the length of into the hypotenuse of a right triangle. This is something we'll be doing frequently in this chapter. In the following diagram, we have several lines on a Cartesian coordinate plane, and what we're going to do for each of them is find the slope. So let's start with our orange line. Now, one way to think about the slope is to consider for each unit I go to the right in x, what is the change in y? So, looking at our orange line, every time I move 1x to the right, how does y change? Y goes up 1. And so we would say the change in y over the change in x. So if y goes up 1, x changes 1. And this is the same all across this orange line. That's why it's called a slope, and the slope is constant. So if x goes up 2, y goes up 2. If y goes up 3, x goes up 3. That's what a slope of 1 means. So we could call our slope a slope of 1. Let's look at our light blue line. When I move x 1 to the right, how much does y change? Well, we notice it's somewhere in here, but we're not exactly sure what this point is of intersection. So we want to find somewhere where there is a definitive point of intersection. Well, if I move 2 x's over, I'm going up 5 y's. So 5y for every 2 x's. And that doesn't reduce any further. Our slope in this case is 5 over 2. Let's give you this green one. What is its slope? What's the change in y for the change in x? So when y goes from 3 to 2, that's minus 1. And how does x change? And x goes from negative 3, or negative 4 to negative 3. That's positive 1 for x. So the slope on our green line is negative 1. See if you can do the red line. What's the slope on this red line? That's right, it's 1 over 1. So you can see that the slope of the orange line and the red line are the same. They both have a slope of 1. And that means that these two lines are parallel. What about perpendicular? Do we see any lines here that are perpendicular? Yes. The lime green and the red line are perpendicular to each other. Notice the relationship. One is the negative version of the other. We'll talk about what rule is operative here later, but I just want you to start thinking about this relationship and see if you can figure out how to make a perpendicular line for any slope. The easy acronym we use to remember how to find the slope of something is usually rise over run. You can also think of it as change in y over change in x. The symbol for change in math is delta, so the little Greek triangle. Or you could say y prime minus y over x prime minus x, or some variant of that. There's 100 different ways of representing it. It's math, so the symbols are of human choosing, but the concept is always the same, that it's the change in the y-axis over the change in the x-axis. That's what our slope is. As another example of slope, let's return to this diagram and see if you can find the slope of the light blue line. To do this, you can move the 5 to the other side by dividing by 5. You have negative x over 5. If you put the implied coefficient before the x, you have y equals negative 1 over 5x. And then let's look at the diagram and make sure this makes sense. I go down 1y for every 5 I move to the right along the x-axis. Is that true? Yes, it is. Down 1 over 5. And so the slope of this equation, and the slope of this line, is negative 1 over 5. All right, let's do one more example. We'll use the same line, but let's use the orange line. What's the distance from this brown dot to our orange line? Now we know that the distance between a point to a line always forms what type of angle? It always is a right angle. Good. And if you want to find the distance, we should we should form a right triangle. Let's form ourselves a right triangle. And so I have this brown right triangle, and it's also an isosceles right triangle, so that allows us to very quickly find the distance between this point and this line, which is 2 root 2. Great, I hope you're getting the hang of how to do geometry on these Cartesian coordinate planes and how to think about it. And we'll call that class for today. Thank you, everybody. Have a good day.